Okay, folks, what I want to go through real quick before we jump into the It's Greek to Me activity, which is our introduction to nuclear changes, where we actually have a change in identity, talking about how protons change in the atom. I'm going to do a quick review of our periodic table and the nuclear symbol, because those are both very important pieces to completely understand before we jump into our next change in the atom. So, again, the first and foremost thing that you want to do when you start to utilize a periodic table is to check out the arrangement of the numbers and the information that is on the table. For each element block, you have your element symbol, you have your atomic number, and remember the atomic number is your number of protons. That's the number of protons right there. That's what makes an atom a certain element. So every atom that has 5 protons in its nucleus is boron. Every atom that has 6 protons in its nucleus is a carbon. If it has 29 protons in its nucleus, it's copper. The average mass, that's our weighted average, where we take the percent abundance of each isotope times its mass, which is protons plus neutrons in atomic mass units. Add those together, so percent times mass plus percent times mass, and we go through that process. That gets rounded, so an average atom, if you're not given a number of neutrons or you're not given a mass for an element, you want to use the average rounded to a whole number. So for mercury, we would round our mass to 201. Okay? Something like carbon that's 12.01 would round to 12. Something like sulfur at 32.07, that would round to 32. We get our protons from the atomic number. We get our neutrons by taking the mass number minus the atomic number. Again, the number of neutrons is mass number minus atomic number. And then finally, we get our electrons from the protons. If the atom is neutral, no overall charge, it has not undergone ionization, then the number of protons and electrons are the same. If we have a positive charge, that means that we lost electrons. So if it's a +1, there's 1 less electron than proton. If it's a +2, there would be 2 less electrons than protons, and so on. If it's a negative charge, you're going to have to add electrons. So with a -1, you would have 1 additional electron, 1 more electron than protons. A -2, you'd have 2 more electrons than protons, and that pattern just follows. For every negative, you have an additional electron. For every positive charge, you take an electron away. Before we jump into the nuclear symbol, I just want to go through a couple things here on the table. First and foremost, our color coding. Anything that's green, which are these 7 elements right here, those are our metalloids. Those are the elements that have both metal and non-metal properties combined together. The ones that have a red bar next to them, which would be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they are what we call the diatomic elements. And diatomic elements are elements that bond to themselves. So anytime you have hydrogen, just elemental hydrogen, it actually exists as 2 hydrogens bonded together. Okay, it's 2 hydrogen atoms floating around in the environment together. Same thing with oxygen. Pure oxygen is 2 oxygens double bonded together. So you end up with 2 oxygen atoms stuck together, floating around through the environment that they're in. Something like nitrogen. It also exists, and this actually gets triple bonded together. So we have 2 nitrogen atoms that are floating around in the environment together. And we'll go over single, double, and triple bonding as we get into the actual bonding chapters coming up, but that's what the diatomic piece means. These 7 elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, in their elemental form, exist as pairs of themselves. They float around, connected to themselves together. Now, the last thing that I want to focus on before we jump into our activity today are these groups and elements that have the orange bars or the orange circles on them. So group 1, group 2, silver, cadmium, zinc, aluminum, and boron. Every element in group 1, when it gains or loses electrons, always loses 1 electron, and it always has a +1 charge, all the time. So everything in this first group of elements, this vertical column, is going to have a +1 charge all the time when it ionizes. Everything in group 2 will always have a +2 charge. Silver will always be a +1 when it ionizes. Cadmium and zinc will always be +2s, and aluminum and boron will always be +3s. Every other metal, if our metal is not in group 1 or 2, if it is not silver, cadmium, zinc, aluminum, or boron. So every other metal, with the exception of group 1 and 2 and the 5 orange bar metals, silver, cadmium, zinc, aluminum, and boron, have multiple charges. So in order to know which version of the ion we're dealing with, to figure out how many electrons were lost from that atom in that circumstance, we use Roman numerals to tell us the charge. Okay, we use Roman numerals to tell us the charge. And the way that that works is if we have something like iron, I can't just say the iron ion, because there's actually 2 versions of it. There's Fe +2, and there's Fe +3. So how do we know? We can't just say the iron ion for both of those, because we won't know which one we're dealing with. So in order to differentiate, to point out the one we're working with, you use the number, the size of the charge, and that becomes a Roman numeral in the name. So if you see iron 2, that means that iron has a +2 charge. This one would be iron 3. The 3 tells you the charge of the iron, or how many electrons were lost. So iron 2, because Roman numeral 2. Iron 3, because Roman numeral 3. And just so we're clear, and we know the numerology, a single I is 1, a double I is 2, a triple I is 3. So 1, 2, 3, and then 5 is V. Okay, a V is 5. So 1 before 5, IV is 4. 5 and 1 is 6. 5 and 2 is 7. And those are the only ones we need to know. I, 1, double I, 2, triple I, 3. IV is 4, V is 5, VI is 6, and V double I is 7. Okay? So any metal between, not counting group 2, but between group 2 and the metalloid staircase that does not have the orange bar, so these are the exceptions. We don't need Roman numerals for these 5 metals. Everything else from group 2 over to the staircase, that includes all of these guys down here, you would have a Roman numeral in the name to tell you what charge that atom has in that circumstance.
Okay? Roman numerals are only used, they're only used for metals that are between group 2 and the staircase. Alright. Nuclear symbols, just to clarify. This is the charge. Okay, that's the charge. In this case, a minus is the number of electrons gained. Whatever your plus is, that's the number of electrons lost. Okay? Then we come over here, this bottom number to the left. This is your atomic number. And that's your number of protons. Okay, that's the number of protons. And then up here at the top is your mass number. This is the number of protons and the number of neutrons together. So we can use these three numbers to figure out number of protons, neutrons, and electrons. So for this one, we have 17 protons because the atomic number is 17. 37 minus 17, we're going to have 20 neutrons. And we get that by taking our mass number minus our atomic number. Protons is atomic number, mass number minus atomic number is neutrons, and then protons with the charge. Minus 1 means 1 electron gained, so we're going to take 17 plus 1 is going to be 18 electrons. Remember that ionization is backwards. A negative means you gain an electron. If that was a positive one, we would have taken 1 electron away from this number. Okay? What you're going to see today is you're going to see a chemical reaction, but this is a nuclear reaction. So you'll see something like uranium 238 92, and you'll see an arrow meaning this becomes what's over on this side. And there's going to be two components over here. This side is called the parent isotope. This is the material that undergoes the nuclear change. So this is what the Curies observed breaking down into multiple pieces. The first thing they saw was the particle that had a mass of 4 and an atomic number of 2. That's called an alpha particle. Sometimes you'll see an alpha particle written as He42. So what the alpha particle is would be a helium nucleus. 4 total particles emitting out, 2 of them protons, 2 of them neutrons. And then what we wind up with is, if we take the parent and remove this, so we're going to subtract these numbers from these numbers. So you're going to take 238 minus the 4 and 92 minus the 2, and that's going to equal our new substance. That's going to give us a mass number of 234 left and an atomic number of 90. So that's going to put us with thorium. This is called the daughter isotope. This is the particle that is made. This is what is produced after this particle has left. So this alpha particle literally leaves. It gets ejected out of the particle, out of the atom. Parent, daughter, emitted particle. This is what's lost. So when you compare this to this, you're taking the emitted particle away. Alright? Now, there's two different forms of decay. You're going to see an alpha decay and a beta decay. The first row on your table is an example of alpha. This is an alpha decay. And then the beta decay is the last row on the table when you look at your Greek to me activity. So as you process through here, if you missed anything or something's not clear, go back, re-watch this, and then what I would like you to do is use this information to either go back and double check the Greek to me activity, or use this to begin the Greek to me activity if you haven't started it yet. We will go in through some notes in more detail tomorrow about nuclear changes specifically. Until then, work through the Greek to me activity, everything but the very last question. You can cross out the if you finish early. Okay? Other than that, everything on the Greek to me activity should be complete by the time I see you next.